All right, let's jump right into this. Welcome to This Explainer, where today we are tackling the absolute core, the defining goal of all machine learning systems. You know, when we hear about AI achieving these incredible feats, like driving cars, diagnosing diseases, or even just recommending your next favorite book, it's super easy to assume the machine has become, well, smart. But what is actually happening under the hood? What is the true north that guides every single algorithmic model ever built? Today, we're going to unpack the exact science of how machines learn, and perhaps more importantly, how we measure if that learning is actually real. And that brings us to a really fundamental question, one that researchers grapple with constantly. How do we know if an AI has actually learned anything at all? Think about a computer that perfectly answers every question you throw at it. Has it truly grasped the underlying concepts of the universe, or has it just cleverly cheated by memorizing its training data? It's a massive distinction. Because if a machine just memorizes things, it's essentially just a glorified database. But if it truly learns, it becomes something infinitely more powerful. It's exactly like a high school student cramming for a massive test. Memorization is like that student recalling a practice test perfectly. If the teacher uses the exact same practice questions on the final exam, sure, the student gets an A+. But what if the teacher changes the numbers or asks the question just slightly differently? The student fails. True learning, on the other hand, means understanding the foundational concepts well enough to pass that final exam, no matter how the questions are phrased. In machine learning, memorizing the practice exam guarantees failure in the chaotic, messy real world. So to understand how we push machines toward true learning, we first have to look back at how we used to program them. Section 1. Beyond hard-coded rules. Let's talk about the limits of heuristics. You see, before modern machine learning really took off, we relied on heuristics, and honestly, they were incredibly brittle. Early computer scientists tried to tackle complex problems, like recognizing handwritten digits, by writing these handcrafted if-then rules. So, for example, if there is a loop at the top and a straight line at the bottom, it's a 9. Sounds logical, right? But in practice, human handwriting is a mess. This approach led to a massive proliferation of rules, and then exceptions to the rules, and then exceptions to those exceptions. It invariably gave pretty terrible results because hard-coded rules simply break down in complex environments. The real world is just way too nuanced for simple if-then statements. We needed an adaptive approach, and that adaptation is the absolute foundation of modern AI. Let's explore where that actually begins. Moving into Section 2, the training phase, and specifically supervised learning. So, how do we actually train these adaptive models? Well, the most common way is through something called supervised learning. This is basically an environment where a teacher provides the exact right output for each training example. Think of it as an algorithmic approach using labeled data to estimate a map between an input and an output. The machine takes a guess, the teacher says, nope, wrong, the answer is actually this, and the machine adjusts its internal parameters. It's essentially a mathematically rigorous version of trial and error. Okay, so what are the raw ingredients of this training? We need a few key components to make this work. First, we have n examples of data, basically a massive input matrix. Next, we break that data down into feature vectors. These are the individual traits or characteristics that the machine is actually looking at. Then we have the target vectors, which are the known categories or labels that our teacher provides. Finally, and this is absolutely crucial, we have the loss function. This is a mathematical formula that strictly measures the error between the machine's prediction and the actual correct target. The entire goal of the training phase is for the machine to relentlessly minimize that loss function. But here is where our story takes a bit of a dark turn. Because as the machine tries to minimize its errors, it can very easily be led completely astray. Section 3. The overfitting trap, or the dangers of memorizing the noise. You've really got two extremes here, and you want to avoid both of them. Overfitting occurs when a massive, highly complex model fits the training data almost too well. It essentially memorizes the noise, the quirks, and the specific random errors of the practice test. It creates this very dangerous illusion of a model that has learned perfectly, but I promise you it will generalize incredibly poorly to new data. On the total opposite end of the spectrum, we have underfitting. This happens when a model is just too small or rigid. It's exactly like a student who simply fails to study at all, completely failing to capture the underlying characteristics of the data. Both of these scenarios guarantee absolute failure out in the real world. To escape these traps, engineers have to carefully navigate what's known as the bias-variance trade-off. This is the ultimate technical balancing act. Bias is the expected difference between the true output and the predicted output. So if a model is too simple, it is highly biased, meaning it's always systematically missing the mark. Variance, on the other hand, is the variability of the predicted output. If a model is way too complex, it has high variance, wildly overreacting to every bit of random noise in the training data. The entire goal is to find the exact sweet spot right in the middle, a model complex enough to actually see the patterns, but simple enough to ignore the useless noise. And finding that sweet spot leads us directly to the climax of this explainer. It's the central focus of everything we've been discussing today. Section 4. The true goal. Generalization. Visualizing this makes it so much clearer. Notice the black crosses here? Think of those as our training data, the practice test we talked about earlier. A machine could easily draw this wildly squiggly line that perfectly connects every single one of those black crosses. But remember, that would be overfitting. The red dots, however, represent testing data. This is the unseen, unknown, real-world data. The true test of our model is not how well it connects the black crosses, but how accurately it predicts the location of those red dots. Whether it's interpolating between known points or extrapolating way out into entirely new territory, that is the true test. Which brings us to the formal definition. Generalization is the ability of a model to correctly categorize entirely new examples that differ from those used for its training. And I really want to emphasize this point. Generalization isn't just a nice-to-have feature. It is the central, foundational goal of pattern recognition. If a model cannot generalize, it is practically useless. The entire field of statistical learning theory is built around understanding how to guarantee that a machine will actually generalize to unseen data. And that guarantee, it actually comes from a deeply mathematical place. This quote brilliantly illustrates the foundation of that confidence, formulated by AI pioneer Tom Mitchell. He calls it the inductive learning hypothesis. It essentially states that if a machine finds a hypothesis that works well over a sufficiently large set of training examples, it will also work well over other unobserved examples. This is the leap of faith, backed by some seriously heavy mathematics, that tells us doing well on a massive practice test does in fact translate to success in the real world. But, and you knew there was going to be a massive but here, Mitchell's hypothesis relies on a foundational rule called the IID assumption. IID stands for independent and identically distributed. What this means is that the training data and the test data absolutely must be drawn from the exact same underlying probability distribution. If you train a model to recognize apples by showing it thousands of red apples and then test it on green apples, it's going to fail. The practice test and the final exam have to cover the same subject matter. If the world shifts and the data distribution changes, the machine's ability to generalize completely collapses. So, knowing the traps and knowing the ultimate goal, how do we actually build systems that succeed? Let's transition to the practical strategies researchers use to force the machine to generalize instead of cheat. Section 5. Achieving the unknown. Let's look at the practical strategies. The absolute most fundamental strategy is strict data splitting. We never ever let the machine see all the data at once. First, we use a training set for the machine to actually learn from. Second, we use a validation set. Think of this like a mock exam. It helps us estimate out-of-sample accuracy, allowing us to tweak the model's parameters and select the best approach without ever touching the final exam. And finally, we use the test set. This is purely unseen data used for the absolute final evaluation. If you cycle back to training after seeing the test set, you've leaked information and your generalization metric is entirely corrupted. And beyond just splitting the data, engineers use a very specific toolkit to actively force generalization. They use things like cross-validation to simulate unseen data across different folds of the dataset. They use regularization, which is a mathematical way of penalizing extreme complexity, literally punishing the model for drawing those squiggly, overfitted lines we talked about. In neural networks, they use dropout, where they randomly turn off parts of the network during training so it can't just rely on memorizing specific neural pathways. And they use inductive bias, applying prior human assumptions to constrain the model's flexibility. It's fascinating because sometimes, to help a model understand the big picture, you actually have to restrict its freedom. Which leaves us with a final, pretty provocative thought to chew on. We've seen that generalization is the central goal of machine learning, achieved through strict mathematics, penalized complexity, and incredibly careful data curation. But think about humans. We generalize effortlessly. A toddler can see one cartoon cat and almost instantly recognize a real-world tiger as a feline. If algorithmic generalization requires such intense, heavily managed statistical probability calculations, just how vast is the gap between a machine's data-driven predictions and true organic human cognition? Are they actually learning, or just calculating the absolute most probable unknown? It's definitely something to think about the next time an AI perfectly recommends your next watch. Thanks so much for joining me on this explainer. I'll catch you next time.